Oh, hello, everyone. So we're starting chapter 7 here. And chapter 7 is on functions. So this is a continuation of we talked about relations in the last chapter. And now we're going to focus on special types of relations called functions. Okay. And this first section, 7.1, are some definitions and notations, and then we're going to go and look at some properties of functions and operations, such as compositions and finding inverses. Okay, so functions are familiar to us because we've been working with functions. You've been working with functions since you did algebra, and I thought after algebra, once you learn about the function concept, is so in everything that you've done. So kind of everything's math is the type of math that you've learned so far has to do with functions. So this is a pretty familiar topic. So there won't be much new here. Again, we kind of put a discrete math spin to everything that we're learning, but we're going to talk about things that are pretty familiar to all of us. Okay. So first, the definition of a function. So function from a set A into a set B is a relation from A to B, such that each element of A is related to exactly one element in B. So that's sort of why it makes it a special kind of relation, because each element of A is related to exactly one element of the set B. Okay, so that's a kind of a condition that we need for it to be a function, right? The set A is called the domain of the function. Set B is called the codomain of the function. So each element in the set A in the domain must be related to some element of B in the codomain. So those are like another condition that that a function needs to be fulfilled, which we probably didn't spend that much time in algebra talking about this. The second condition, the phrase is related to exactly one element of the set B, is the one that's like you're checking to see if it's a function or not. We're going to kind of look at examples where something is not a function because the first condition is not fulfilled. So both of these conditions need to be fulfilled in order for a relation to be a function. Okay, so first one is that each element in the domain must be related to a certain element of B, so you can have values in the domain that are unused. And each element in the domain must be related to exactly one element in the codomain. Okay? All right, so let's look at some examples. All right, so first example, we're given our domain, our set A, and our set B. And S is a relation, which is given by coordinate points, and we're trying to figure out if it's a function from A to B, right? So one way of representing a function is just through coordinate points. So we'll see other ways, we'll encounter other ways, again, that you're familiar with: graphs, equations, tables. So this one is given as coordinate points. Okay, so we need to check both conditions above. Okay, so the first one is, are all the values in the domain used? Okay, so are all the x values in set A in the domain used, right? Because that's what that says. Each element in set A must be related to some element in B. Okay, so if I look at my coordinate points, I have -2, -1, 0, 1, and 2. So all the values in the domain are used, so that condition is fulfilled. Okay? All right. Second condition is that, right, each element in A is related exactly to one element in set B. Okay, so the -2 would only be related to one value in the codomain. It can't be related to more than one value in the codomain. Okay, so each x is related to only one y. Okay, so I'm kind of using the standard notation. So x is in A and y is in B. That's kind of natural name to go to because we're used to xy values, right? And this one is also correct. Okay, so this is a function. This relation is a function. Okay, in this example, we have R is the real numbers. Okay, then we're going to look at this relation right here. Okay, so this is a relation defined in set builder notation. Okay, so this says that it contains pairs of points x, 3x. Okay, so basically inputs the x values, the outputs are going to be 3 times the input values, where x is a real number. Okay, so this is a relation that's going from the real numbers into the real numbers. So that's the domain and the codomain. All right, so we can see that this is a function because, again, the first condition is fulfilled. All x values are used because the inputs are the general x such that x is a real number, so we input all the real numbers in there. Okay, and also the second condition is fulfilled because if you input an x value and you output 3x, for each x value you're going to have only one y value that's equal to 3 times that x value. Okay, so there's no way that x could be associated with more than one value of y. Okay, so this is also a function. All right, so let's look at another example. Okay, so we want to determine if f is a function. We're going from the set of integers to the set of integers. If f of n equals plus or minus n. Right, so we see that like the first condition is fulfilled. Basically, we are using all the integers and we can get an output, so that one's fine. But the second condition is not fulfilled, so this one doesn't work out. Because if I put an integer as my input, then I could either get the positive or the negative of that integer. So for example, if I put in 2, I could get positive 2, or I can get negative 2. So that breaks that condition that for each x, there needs to be a unique y associated with it. Okay, so this is not a function. All right. Let's look at this one, 1 over n squared minus 4. Okay, so let's look at the first condition. So first condition is, can I use all the values in my domain? Okay, so my domain is the set of integer. So you can see that this gets broken because I can't use all the values on the domain. And specifically, there's a problem if n is 2, or if n equals negative 2, then the fraction right here is undefined. Okay, so the way it's written, that this function right here goes from the set of integers to the set of integers, and this is the formula, this is not a function. Okay, if I were to change the domain, if I were to say that the function is going from the integers to the integers, but 2 and negative 2 are excluded, then it would be a function. But sort of sometimes you need to restrict the domain or specify the domain a little more detail in order to make it a function. Okay, so there's a small adjustment that you can make if that first condition is not fulfilled. All right, so let's look at a couple more definitions. So first one says the set of functions between two sets. Okay, so given two sets A and B, the set of all the functions from A to B is denoted by set B to the A. And next, the definition, we're going to define the image. It's the image of an element under a function. So if I have a function that goes from set A to set B, let f be a function from the set A into set B. If A is an element of the domain, then f of A is used to denote that element of B to which A is related. So that f of A, or the y value, if we're going to talk about x and y stuff, is called the image of A. Or more precisely, we say that it's the image of A under f. Right. So basically we have our input is the A value, and the output after you apply the function rule is called the image of A under f. Okay, so we write f of A equals B to indicate that the image of A is B. Now, here's another definition, the range of a function. Okay, so the range of a function is the set of images of its domain. Okay, so if I have f goes from set x to set y, then the range of f is denoted by f of x. And you write that f of x is the set of all images, right? So all f of a's where a is part of the domain, or you can write it as all the b's which are in the codomain for which there exists an a in the domain such that f of a equals b, right? So the range is a subset of its codomain. So like the codomain of a function is the set of all possible values that could happen for the outputs. The range is a subset. The range is the actual values that happen that you get for the outputs when you plug the inputs in. Okay, so the range is a subset of the codomain of a function. Okay, so let's look at this example. So we want to find the domain and the range of each of these functions. So let's see. Okay, so part A, it says I'm looking at the function that assigns to each non-negative integer its last digit. Okay, so basically this says that if I have a non-negative integer like 254, this is my input, or keep using x's and y's, so it's fine. Okay, then the output is the last integer of that number. So the output for this one would be 4. Okay, so my inputs are integers and my outputs are the last digit. Okay, so you can say the domain is all non-negative integers. Okay, so these are going to be positive integers plus 0. Okay, and the range, what comes out, are the integers from 0 to 9. Okay, so the range is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are my only choices. So even like the codomain of the function are integers, the range that once you actually pull out are the last digits of a number. They're going to be from 0 to 9, all the integers from 0 to 9. Let's look at the next example. The function that assigns the next largest integer to a positive integer. Okay, so this one, it says that, let's say I have an integer like 13. This is my input, and my output is the next largest integer, which is 14. Okay, so this is like the function x plus 1, right? So if you kind of plug in x, then you get the next integer x plus 1. Okay, so my domain here, it says next positive integer. So again, I want positive integers to be my domain, right? So, positive integer, sorry, so it doesn't include the 0. So my domain is just the positive integers, okay? And my range is positive integers. The domain is going to start with 1, okay? The range is going to start with 2, okay? So it's going to be the positive integers without that first, so minus the element 1. So it's the positive integers that are bigger than or equal to 2. All right, let's look at next one. The function that assigns to a bit string the number of 1 bits in the string. Okay, so bit strings are strings of ones and zeros, right? So let's say I have 1, 0, 1, 1, 0 is a bit string. Then the output is 3. The output is the number of ones in the string. Okay, so this one, the domain, I don't have a shortcut for it, but this is domain is the set of all bit strings. Okay, and the range is going to be a positive non-negative integer, right? Because it could have 0 ones in there too. All right, let's look at D. Similar thing, the function that assigns to a bit string the number of bits in the string. Okay, so we sort of have the same example. 10110 could be an input, a bit string, and the output is like how many bits do I have in this string, and there's 5 of them. Okay, so again the domain is going to be the same as above, the set of all bit strings, and the range is going to be non-negative positive integers, because I can't have a bit string of length of 0 because it wouldn't mean anything. Okay, so the lowest number that I can get for D is a 1. Okay. So let's look at example 5. So we have 3 functions here, and we want to explain why these functions are not a function. These relations are not a function from the real numbers to the real numbers. Okay, so let's look at the first one. Okay, so 1 over x. Okay, so this one breaks the first condition that says that you need to use all your the elements of your domain. Okay, so here my domain is listed to be the real numbers, but you can't use x equal to 0, so that breaks the first rule. So the first rule is broken. So this is not a function over this domain. Okay, so it can be a function over the domain of the real numbers without x is 0, but it's not a function over the domain of real numbers. All right, let's look at the second one. F equals square root of x. So same argument here, because I have the domain is listed as my real numbers, right? But x can't be negative, so we can't use negative values for x. Then condition 1 is broken, and that's not a function either. Okay, easily fixed by making the domain of this to be all the positive real numbers. And f of x is plus or minus square root of x squared plus 1. For this one, the first condition is fine because I can use any value of x, but the second condition is broken because it's double valued. Okay, so for each x values, you're going to have the positive and the negative of the square root. So this one is that for each x value, you have 2 outputs. So that condition is broken. All right, so this is the section 7.1. Next section, we're going to look at some properties of functions.